It's been a long day. Satoshi and I are batting cleanup, which is, I guess, not a cricket term. It's an American baseball term, but it means that we're going to be at the end here. And so I hope that you're willing to interrupt me with questions if you have a question. So let's not wait to the end. If this is an eager group, if you're partway through and you say, wait, I don't understand, or oh, what about this? Please go ahead and ask. So we're going to talk about something that was already introduced. Manish introduced this idea of the continuum, but I want to dive into especially the edge part and what that means and what that computing might look like. So this is an example of a very, very large instrument in the United States. This is part of the NEON project. It's studying the ecosystem across the United States, and there are things like this around the planet. New Zealand has things like this. The other parts of the world have this. And the concept here is that there's a monitoring station, and then there's an instrument hut where all the tech lives that monitors the atmosphere, in this case, atmosphere, ground, other things. And there are about 80 different sites like this around the country, and they study different biomes, different parts of our United States and the planet. And they're designed to give us an understanding of what's happening as climate changes and as humans influence our planet. Now, the way yes, question?
Those instruments.
So that is by the National Science Foundation, that project that's called NEON, and you can look that up. It's a multi-year project. Those kind of installations you don't just put up for a couple years and tear down. So it's a long-term facility, as it would be called in the United States. And so this is sort of the classic way that that kind of data was processed. Someone uses an instrument. They would write it down in a notebook. They would then take it to their office and they'd study it, right? This is Katherine Johnson, worked in NASA doing analysis of paths, satellites, or space paths and so forth. And we've improved on this greatly, and our world now looks something like this. Right? Where so now at the edge, we might have IoT devices, we might have SKA, we might have gigantic telescopes, we might have microscopes, LiDAR, radar, everything. And we want to pipe that all the way, and this is the continuum that Manish mentioned, all the way to the supercomputer center. However, there's a problem. And that problem is that our instruments are way more capable than we can ever, this is an important part, ever build our network. So, whenever I talk about something like this, people say, well, what if we had 5G? What if we had a faster network? We will always have more instrumentation than we have bandwidth, because we can build thousands of these, and we have to compress. And we heard the talk earlier about FPGAs and how we might do that at the edge. So this is our problem. Now, the difficulty here is we want to analyze the full resolution bandwidth. We also often have a latency problem. We have to make an answer very quickly. And we can push experimental control back out to the edge. Now, right now, all of these things are built custom. Every science group builds their own custom way to try and manage computation that has to live at the edge. So the project I'm going to talk about is an infrastructure project to design something that's reusable, that gives us something at the edge that can be reused against dozens or hundreds of different kinds of instruments, and yet still work and compute and bring stuff back to the supercomputer. So this is that project. It's funded by the National Science Foundation. It's called SAGE, and it really builds on about 10 years of work. So we kind of started Skunk Works about 10 years ago in 2013. This summer will be the 10th anniversary of that. And it started with just a handful of students when we were given a hyperspectral camera. And we were told, hey, this is a great device. Can you guys set it up, put it in this field? We want to measure photosynthesis. We think different spectrum of light will tell us whether the plants are doing photosynthesis. And we tried to get the data off this hyperspectral camera and realized that it's way too much for us to send back home. So we would need to move the computer to the device. And so that started this path of how do we move computation to the device. Now, it isn't just physically moving it to the device. There's more to it than that, and I want to talk about that. So these are the goals of the project. It's to build this cyber infrastructure where, just like that neon hut that I described, we want to take parallel computation, move that into that hut. Now, the reason that's so important, just to give you another example of the bandwidth problem, a classic thing that happens in these huts is that there's a sensor that could be sampled at 40 hertz. Now, that's not blindingly fast. 40 hertz is slow, right? Yet the environmental scientists still take 30 minutes of 40 hertz data, smooth it all out, and report one number. Okay? So they report one number for 30 minutes when they have 40 times 30 data points, right? So any really interesting thing that happens is gone, right? They're getting a wonderfully, wonderfully smooth average, right? So that's just one example of the kinds of things that if we move computation out here, what we can do. So the concept that when we first started was we're really writing what we might call a software-defined sensor. There is no such thing as a coyote sensor. I can't go buy a coyote sensor. I can, however, write an AI algorithm that I put in a computer next to a camera that is a coyote sensor. So I can find coyotes, or I can find cars, or look at two different species of plants. So I'm writing a software-defined sensor, and I can load those sensors up dynamically out to the edge. And we do that by using all the standard software tools that you know, Kubernetes and Docker and all of those pieces, and we load that container into something that's at the edge. Now, it could be a rack-mounted server. It could be this kind of special purpose device that we have here. So this is a table from a paper we're writing. I realize it's sort of black and white, not so exciting, but it shows all the kinds of sensors that people have written already using this kind of style with us, right? So over here, we have motion analysis, solar irradiance, estimating the water depth. This tells us what is the AI methodology, whether it's using a predefined system like YOLO or ResNet 50, or is it designing their own piece of software using phase correlation? And then over here are where is it running in the country. We now have these sites up running in Colorado, in Texas, in Oklahoma, in Oregon. We just have one up now in Hawaii. We have 10 that are in Australia, although they seem to be slow in turning on the power, so we're waiting for them to come up, but we hope that they'll be up any moment. So what does it look like to have an app? So as I said, you're running your container out at the edge, so that means that we can write ourselves a software-defined sensor. We write an app, and so this is our app store. So this is, if I go to portal.sagecontinuum.org, I get a list of all the apps that someone has built for running out at the edge. So, and I'm going to run through some real examples here, but here is like surface water detection. So if you were to click on this, this was updated quite long ago, but some of these are updated, days ago. Here's one that's been updated 23 days into this particular branch. And so if you grab one of these packages, it's a Docker container that has special methods for grabbing data from the sensor and pushing data up to the cloud and running that inference, whether it's doing federated learning on the edge or it's just running pure inference. So from a high-level perspective, this looks like two things. Something that's happening at the edge, and this is, again, that stack that I mentioned, a very, very straightforward stack. However, there are some unique things about the edge. I'm going to mention that in just a moment. And then, of course, we push data. It's not surprising. We push data into the cloud. We stick that in a database. That database can be queried, and people can get live hooks on the data so that things can be triggered if something interesting happens. So this path here of something at the edge, pushing into something in the cloud, if you and your graduate students were in a workshop for about 3 or 4 days with a whiteboard and a pen, you probably would have the same design, right? I mean, it's pretty straightforward. The difficulty comes at some of these things that define uniquely what edge means. So what is that? Well, so we learned earlier from Karen that a digital twin is not an HPC simulation. That's not enough, right? It has these two features, right? It's a simulation of an instance, and it's updated dynamically, right? So edge does not mean that I took a server and I put it in a truck and moved it somewhere else. That's not sufficient. There are a couple things that are really important and are different about computing at the edge. So let me walk through those. This is an important part to understand sort of the challenges if anybody wants to try this or use it. So the first is that we have an extreme cybersecurity problem. And I say extreme because normally, if I go to Catalyst Cloud and I want to walk in and hack something, the first thing that's my impediment is there's a locked door. And I can't go to the server because there's a door. For edge devices, there often is no door, right? In the city of Chicago, we have nodes. The city told us to put it on a pole high enough so you can't hit it with a hockey stick, right? So that's our only barrier, right? It's Chicago, right? Just enough so you can't hit it with a hockey stick. So I'm missing the physical security of just hitting a door. The next problem I have is that there's no network security. So again, even if you're in a place like this, there's a set of firewalls, there's a set of routers, there's a set of pieces of software that detect intruders. If I'm out on the edge, I don't have any of that. I'm sort of exposed using some form of networking to immediately the wild, woolly internet. So how do we treat that then from a design perspective? So the first design decision we make is that there are no open ports. It only phones home. So again, it's always bad in cybersecurity to say you can't hack into the device, right? That was always a bad idea. But I feel pretty confident that if I put a node on the table, that it would be very hard to get in because there are no open ports. All it does is phone home. So it's very similar, if you might think about this, to maybe your connected watch. My watch connects to my phone here, but it's not sitting there with an open port where someone can SSH into my watch, right? That's not how it works. So not phoning home is a great cybersecurity. Incredibly complicates our software stack, right? Now all of those standard services, Kubernetes, all of those things that you might want to think, oh, I just connect with a port, now I can't do that. The other thing is that we have to make sure that apps can't leak data. What I mean by that is that there's a social contract with a group if you want to put your instrument in a way that they can run software on it. So if I'm on a mountaintop in Colorado and I say, oh, I want to let you run your software to detect interesting clouds going over. You say, great. But now there's a contract there, which is I don't want you to take any other data and ship it off to a website in Idaho that we've never heard of before, right? I want to control all the data so I can essentially get a transcript of every packet that left that edge device so I know for sure where it went. So we have a set of very strict rules that you can't exfiltrate any data. Everything goes through a standard pipe that is locked down that we know. So we can see what leaves a node. And finally, of course, full encryption. So I spend a lot of time on extreme cybersecurity because that's a hard one when you have sites distributed everywhere. The others are easier. So autonomy is pretty easy. Networks go down. Your edge has to keep working. Probably weeks, maybe even months. We've had nodes that go off the air because it's a cell phone network and the cell phone tower, something changes in the tower, it loses its connectivity for weeks, comes back online, and all that data is queued up and gets pushed out, right? So that kind of autonomy that it's doing the right thing, maybe just not collecting data, but scheduling jobs, running things. Multi-tenancy. In these cases, most of these nodes need to be shared among scientists. If you have a node on the top of a mountain, you might want to use it to count coyotes and look at weather and understand rain patterns and bats, but it's not a single-purpose device. So it has to support multiple tenants. And finally, the apps themselves need to be built in a way that's reproducible. And this is because scientists are used to having a device that they buy, some sort of, like say, a rain gauge, and it sits there and it delivers data and it never changes. But if I can upload a new container every 10 minutes when my grad student has a new idea, now there's a problem, right? What's my data stream look like? It's changing all the time. So we need a method by which the program, the AI model, and all of the pieces are sort of versioned and stamped. And Paolo talked about this with Pachyderm as an example of a way to do this. So we need that, and we do that by building everything in the cloud and then shipping the container out to the edge. So a user doesn't get to ship their container to the edge directly. They have to put it into our system, which versions it and then ships it out to the edge. OK, so now let's look at some examples. So the software stack runs either on a standard x86 box, which is down here, like this Dell. I'm sorry, it's not an HP, but we can fix that. We can fix that. Here we're installing it in a small hut, a little instrument cabinet. Here's one going up in Chicago, and the bucket truck is lifting it up here. The CDOT electrician will strap it onto the pole with a couple stainless steel straps. It has an LTE modem, and it starts transmitting. Again, phone's home. There's no open port. So when we see it, right? It connects to our server, and suddenly it's talking. So what can you do with things like this? Well, this is an undergrad project, which is really fun. They put a node right in front of what should be a crosswalk. And then, again, because they're preserving privacy, they're using AI to only look at whether someone is walking away from the camera or walking toward the camera. That's the red and blue. And they can see who's crossing the crosswalk directly, who goes up to this corner, how often, and they put that live on the net. So you can no people image is live on the net, but the response of who's using it and how. You can also modify the behavior of LiDAR. So this is an experiment in Oklahoma. These LiDAR are about $100,000, $150,000. And one of the problems in these kinds of instruments, again, there's way more bandwidth, or way more instrument than you have bandwidth. So they load into the instrument a simple averaging function that looks for interesting features. But if you move our GPU and put it out with the LiDAR, we can find these problems here and report back the real data that a scientist is looking for. Again, finding the full resolution of that data. This is an example of the cloud motion vector that I mentioned. Camera looking straight up, running an algorithm, calculating where the clouds are moving and getting this motion vector, then using self-supervised learning to discover the patterns, and then using this for LiDAR and other atmospheric science. So this is a bird, and this is the FFT, right? The spectrogram of bird. It's kind of hard to see, but I wanted to put it up here so there's a little bit of fun here, which is that we're using the Cornell Bird Network, which is Cornell is like the on the U.S. side has the ornithology department that studies and provides interesting apps. You can get an app for your phone called Merlin. You go outside and you listen, and it'll tell you what bird you're hearing, right, by loading it up on your app. Definitely should try it. It's a lot of fun. So we have that app, and we've essentially put it on our nodes. Now here is a bird making a certain sound. It's kind of hard to see because this is not colored so well for this. But right here, you see that there's a bird, and there's another bird at this exact same moment. And if I go forward here, there we go. This is that other bird. So the AI problem for us is each of these SNPs represents a sample. You're trying to find samples that are not overlapping with each other, and then identify what the species is. And here's yet another bird species, and then plot that. And so we have one of these running out at a prairie. It's running, well, it's actually running in many places around the country, but one example is over here near Chicago. And you can see here the different birds that we can identify. And this is also near Morton Arboretum, which is a large forest near us. And what this allows scientists to do is, again, they've written a software-defined bird detector. And as the AI algorithms improve, our ability to understand what's happening at the edge improves. And what this allows for computer scientists is it's a test bed. I can write myself a new code, ship it out to a forest, have that code analyze the data, and then tell me how I'm doing, right? And this is using a self-supervised method rather than the current method, which had experts, again, to try and find clusters, find birds, and then use that to identify. This is a classic problem of determining how deep something is. Now, environmental scientists stick these poles in the ground. I've been pained by the fact that they decided to use white poles to detect snow. You know, from a computer vision perspective, orange and black, you know, orange and blue, red and yellow, I don't know, but white. But this is a great problem that normally a grad student would walk out there, look at the markings, and say the water's this deep, right? So now someone can write a piece of code, and this is one of my postdocs, Songha, who wrote a piece of code. It looks at the stick. It's calculating here, trying to calculate the water depth. And as the AI algorithm improves, we will then be able to build models, hydrology models, that are dynamic. They can look at bridges, they can look at sticks, they can look at rivers, they can look at things floating in the river to understand how fast the river is going. All of this is possible by moving AI out to the edge. The same is true for surface water. Flooding in cities is a big problem. Again, you can look at the edge, load these codes up into the edge, and run them. Traffic, of course, is an obvious one, but still is very important. Most of the original traffic work is on understanding, you know, flow. But one of the things that we can do is understand interaction, right? Dynamics. You can understand, is that a delivery vehicle? Is that a bicycle interacting with a car? What might that mean? We also have work that we've been partnering with others in wildfire. So this is with the University of Oregon. It has a hazards center, and also Ilkay, who couldn't present, has a wildfire center in Southern California. And the concept here is straightforward. Can we use AI to determine what is a fire? So we had this wonderful opportunity because, you know, fires are rare, but when it's a prescribed burn, we could set up ahead of time. So we set up, in collaboration with Colorado State, we set up a node, several nodes, at a prescribed burn. So as they started the fire, we now have an infrared camera and a visual camera running. And so now the infrared camera can be used to train the RGB camera so that you can see, okay, this is actually hot plume, right? This is a hot plume. This is what it looks like because we know the temperature of that, right? So we can move these things also out as experiments. And that data is available. So if other people here, we had that node up for several days, detecting what the bird calls were before the fire, what the bird calls are after the fire, what the air quality looked like before the fire, what it looked like after the fire. All of those things are possible by processing that data immediately in line. Another example is a new project that we started with the Ojibwe tribe. This is a sovereign nation in the United States, much like you have here in New Zealand. And one of their sentinel important species is wild rice. It's not actually rice, right? It's a different kind of grain, but it's harvested and eaten. It's an important food source. There's a picture of it. And we, through about a year of effort, luckily there are experts at Northwestern University who have been working with the tribe for quite some time, got permission from the tribal elders to put nodes in the territory and help and start to understand what is climate change doing to monumen, which is their word for wild rice. And so we can do that by building cyber infrastructure. And now there's interesting data sovereignty questions here. And so, you know, if there's time, I would love to be able to talk about those. But from a computer scientist perspective, the idea that the data doesn't automatically come back to our server and go out to the entire world, where we might have to share sovereignty or understanding of rights to that data that's collected on their on their territory is an interesting there's computer science, there's policy things that I can't really, I don't really know so much about, but there's good hard computer science problems. We've also set up a way to launch these things in a mobile fashion. So this is a mobile tower that's what's called ballasted. So it's just big cement blocks on the bottom. So you can drive this out in a pickup truck. You don't have to drill any holes. This is particularly important for that Ojibwe tribal nation because we have to restore the land back to its original state when we finish our experiment. And we can do that because we're not pouring concrete in the ground. So this goes up. This particular one has a Starlink terminal that we've welded on the side here. And so we have networking because this is an area in Montana where there's just nothing around. You'll see here in a second. And now we can monitor that space with infrared and with the camera and with audio. And again, the point here is to make a cyber infrastructure that computer scientists and experimentalists, people here, could write their own code and upload it into these nodes here and run it and test out their newest algorithms. So this is an open infrastructure that allows people to run their own codes in those nodes. So how do we run code in a node? Well, we have to have a scheduler of sorts. And so this is, again, a little different than our standard HPC scheduler. Our standard supercomputer scheduler is one where I throw in a job and then I wait a few hours or a few days, or I get dinner and maybe I come back and it's going to run. There isn't any real-time issue unless you're doing the urgent computing that Manish talked about. If I have to wait 2 hours or I have to wait 2 days, it's inconvenient, but it's not going to hurt my science any. That's not true at the edge. So that's why I mentioned that the multi-tenant scheduling is a tough problem. So it's more event-driven at the edge. Things like this particular example here, which is we're going to run a sampler which is going to grab an image only when the object counter says I have a car and maybe I have a pedestrian, right? So I want to look at interactions between cars and pedestrians, for example. So I can write that kind of logic so that I'm only scheduled on the node, like a job scheduler. I'm only scheduled when something interesting happens. Or maybe I only do something when it's raining. Or I don't check for birds when it's nighttime, right? Or I only look for coyotes when it's at night and not during the day, right? So there are many ways that you might write this sort of event rule-based system. And we have a scheduler that's been designed to run these over time based on those rules. We also need to automatically collect performance data on every one of those edge apps because we have to make an estimated guess. Can we run 2 jobs, I'll say jobs, at the same time? We obviously don't want to sequence them. If we could run them at the same time, they might fit in the GPU at the same time. But we wouldn't know that unless we have some performance data from the past. So we gather that data and we use that so that we can decide here whether to load and launch that application and maybe launch 2 different applications, in this case here, simultaneously because I know they're both small enough given their previous history. Okay, so let's pause for a moment and just talk about the hard science problems that we have. So that was the backdrop of what we have for edge computing. You have some special concerns at the edge with cybersecurity, with data, with operations, with sharing. And now we want to look at what are the computer science pieces that make this interesting problem for us. So the first is we don't have a programming model. Okay, so we all know how to write, many of us know how to write computer programs for an HPC system. You have a message passing library. You use OpenMP, where's root, or OpenWound, right? You write your code, you have a messaging library, and then you have a job launcher, and then you have to describe how wide it is, right? How many nodes do you have, right? For the Continuum, we don't have something like that. One of the reasons we don't have something like that is we can't, in the Continuum, name individual instances of edge devices. The number of devices is changing all the time. We can't name them all, right? So like we do with our cluster, we always know how many nodes are in it. So we really need to be able to say things like, I want to run this where I can detect wildfire in Colorado. And the number of nodes might be changing all the time. Right? So that kind of programming model is not something we have. I would love to hear from you if you have ideas for what that might look like. That's a hard problem. Another one is that we want to do AI training out at the edge. So if you think of any one of these models, they're trained on a statistical distribution that involves all the data that you've seen. But then you take that model and you run over to Wyoming and you shove it in a node that's on a ranch in a place where it was not statistically trained and represented, and you hope for the best, right? Well, we might be able to do better from an AI perspective. There might be interesting ways to update that model in situ and improve that model. So there are a lot of AI training things that could happen in this space. Self-supervised learning with multiple instruments, like I mentioned with the infrared camera and the RGB camera. So I've trained the RGB camera inference using infrared. We do the same thing with LiDAR. So we have a LiDAR that's, again, 150K. It points up at the sky, and it can tell you exactly what height each of the clouds are at, right? Now, I can use that information to train an RGB configuration to guess at what height the clouds are, because I know what height they are by using the other instrument. So we can build models that do that. So that's an interesting approach that people could explore. This container technology is hard. We're using a variety of interesting Docker containers. This cooperative sharing and multi-tenancy is open, again, a pretty open research area. Control loops for actuation. So I haven't talked much about actuation, but that's another hard problem. We have, for example, that infrared camera has a very simple actuation, which, well, I can pan and tilt it and move it around, which is, if it starts to rain, tip it down like this so we don't get rain on the lens. So we've noticed that if rain's on the lens, it dries and then it makes a shadow. So we just need something very simple, right? Tip down like this when it's raining. When it stopped raining, you can tip it back up, right? So there are all sorts of actuation examples where you rotate, where you see something. A great example is let's say you have an idea that a particular object has 80% likelihood of being the object that you're looking for, right? Well, I can now zoom in. I could change where I'm moving. I could try different things and maybe even do training on the fly to decide that's the same object. I'm just looking at it from 3 different perspectives. Movement, all of our nodes right now are stationary. Obviously, drones and buses and other things would make that a lot more interesting. The real digital twin here, running something and then having actuation, dynamic update. There's also a room for microelectronics. So we've been using standard GPUs, but neuromorphic and other things that could lower our 50-watt footprint for a GPU out at the edge to 5 watts would be spectacular, right? A 10x, then I could start powering things with a small solar panel and not a huge battery bank. And advanced networking. We have a project using 5G and so forth. OK, so we also could go smaller. Back up? All right.
Please, just asking about that little thingy that you have.
Yeah, so this is work with University of Utah. So the University of Utah has a project called Powder, which is to understand and design next generation wireless protocols. And so they have software-defined radios. And so this is a board that's essentially giving you a software-defined radio. And we can plug that into Sage so that the algorithms that are processing the RF data can be processed in a GPU out at the edge. So this is the node that's right now on top of the Utah Field Museum. And you could look at this node and then look at the RF spectrum coming off that, and then you could do some computation.
That's not a bespoke. It's a bespoke chip?
No, this device you can buy. They're expensive and they're strange. I mean, they're bespoke in the sense there's not millions of these that get sold, right? I don't know. The SKA guys probably know that.
So I asked Manish for a discount mentioning your name.
Yeah, you can go look this one up, right? That's okay. The particular part. There's also lots of room, as Dan Reed likes to tell us, there's more room at the bottom, which is that the nodes that we're talking about are fairly robust GPU nodes we also could be plugging in very small sensors. So this was this is one of our nodes, and these are moisture sensors designed by the University or Colorado State. You could put those in the ground to get better understanding of soil moisture, of salinity, other measures, and you could be bubbling that up into a node like this, right? So that's a project that we've just started with Oregon and with Colorado State. Hopefully by this summer we'll have enough students on there that we'll have some great results to share next time. We also have worked on student kits. So the idea that we do have these nodes that we could give you a login and you could develop a piece of code for it, but we'd love students to be able to do the hands-on part. So these NVIDIA Nanos are maybe a couple $100, right? I mean, that was pre-COVID. They're hard to find now, but they'll eventually become easier to find. And with that and a camera and a microphone, you can start putting your Docker containers on there and try your own AI, right? Try your own bird detection or your own automatic system for finding things in the environment or other things. So yesterday's earthquake reminded me of this experiment that happened. This is a true story for us. So when the Hunga Tonga eruption happened in 2022, we were working with seismologists in Oregon, and about 2 days afterwards, they said, well, did you guys see it on your nodes? And we said, well, no, we don't have any seismometers, connected, or we don't have anything connected yet. We were planning to. We work with those guys, but we didn't have anything connected at the time. He said, well, you might have seen it as a pressure wave. And, well, we do have like a $4 barometric pressure sensor, the Bosch, a standard Bosch sensor that measures temperature, pressure, and humidity. And so, Rajesh Sankaran ran off and grabbed all the data from the nodes and started looking at the pressure data. And so here is a node in the center of the country here. And right here, there's this interesting discontinuity. And it matches with the node that's in Texas and the node that's in Oklahoma, and then here's the node that's in Oregon. And that pressure wave goes around the Earth several times from the explosion. So we actually saw it, getting smaller. The pressure wave is getting smaller, but it goes around the Earth. Now, here's our problem again. Remember, I started out and I said, those atmospheric scientists, they have sensors that they could sample at 40 hertz, and they only average it over every, 30 minutes. We were doing exactly the same thing. We thought to ourselves, well, how quickly does the barometric pressure ever change? It's a weather sensor, right? I mean, you might sample this once a minute. So we were sampling it every 30 seconds. So this discontinuity that you see here it was a more than 30-second discontinuity, but imagine if we had been running the anomaly detection that we want to run at the edge, what we would have seen, some really interesting high-resolution data, we would have seen a lot more. So this is, again, a great reason for us that we need to be putting these kinds of smart AI algorithms all the way out the edge, even for a lowly $5 Bosch. Hope no one here from Bosch here, but a pretty cheap, widely available sensor, right? Okay, so now I'm going to wrap up, and sorry, we apologize to Ivana and Eva, but we were talking about how we might extend SAGE and extend what's happening at the edge out to workflows. So one of the things that SAGE does is it draws a pretty strict line that says, okay, I get the data to the database, and then I'm done, right? So edge computing, we get the data from the edge. So here's my GPU. Here's my little wireless antenna. I'm drawing this out at the table back there. It's one of the good reasons for a meeting is you actually have time. If you get a beer and some cheese, you have some time to go back there and draw pictures. So here I've detected bird A, and I send it into my database. And what I want is a workflow system that does more, that triggers interesting events. So for example, could I run a supercomputer computation? And one of the ones that we really would like to run is if we detect something interesting happening in Montana, the wind is 50 miles an hour or whatever, I want to run a simulation right there and then. right? Something interesting. Similarly, if I know, based on a simulation, that it's going to rain heavily in 3 hours, I want to change the way my instruments operate to change what I'm looking for. So that's an edge to cloud and cloud to edge kind of problem. So we would really love to see how to extend what we currently have, which has some pretty strict boundaries. We just dump it into the database and we're done, to really push that into the workflows that could trigger interesting high-performance computing computations. Now, I've been talking about environmental science as a driver. It's an excellent one. But really, they're all over. It just happened to be the one that we started with. This one is at APS, which is a light source at Argonne. It's a gigantic, you can think of it as a super, super large X-ray laser that lets you image things down at the X-ray wavelengths, right? And so what they do is they have a target, they have a set of detectors, and they're getting data from that. And it goes in, and normally they just get all this data into big files, right? What they would like to do, though, is actually steer the beamline. Okay, that sounds like a close-the-loop problem, right? That's an actuation problem. So rather than just send all the data and go out to lunch and 5 hours later come back and your sample that you've been X-raying with this laser is now toast, especially if it's a biological sample, it's just done. I want to find the interesting bits in the right order. So here, right, where they normally left to right, back and forth, of something that they're interested in looking at, and they're building a workflow which uses the same lightweight NVIDIA GPU, for example, out at the edge so that they can put this in their control loop and then decide where to scan. So now hopefully you're starting to think, wow, this is the kind of thing that eventually will be happening at the doctor's office, right? So when you go in for an X-ray, rather than scanning everything at the same level, you can imagine future machines which do an initial scan and then find the area that's most interesting and scan at a higher resolution that area, whether it's an MRI or an X-ray or any kind of imaging. This kind of adaptive AI sampling at the edge could be very powerful. So here are the hard problems. I'm going to pull up a website here in a minute as I wrap up. Here are some of the hard problems I'd love to work on together to solve problems. So one is that hand-scribbled note that I mentioned earlier, sort of the edge to cloud and cloud to edge. Are there new workflow tricks that could go there? What would that look like? How would we close the loop? We've been working with Danielle, who's Manisha's student or postdoc, and I think yesterday we shipped him a server to France. So I'm wondering what the duty on that will be, but. Did it go to Utah? And then is he going to? No, he's going to use it in Utah. All right. So this idea of doing urgent computing and being able to create on-demand workflows for that is an interesting one. I'm going to come to this edge AI application in a minute. Integrating IoT sensors, right? Like this moisture sensor I mentioned. More instruments. We have LiDAR, we have radar, we have hyperspectral, software-defined radios, but there are lots more. And it's all Linux, so you just plug it in, right? I mean, it's not, then the next question is, what AI do you write? Actuation, right? Being able to control things. We're only just starting in that space. We'd really like to have partners and figure out things that to the right sort of actuation. And finally, this is really part of an NSF project, which is building this national infrastructure for AI. And so we want to keep pushing on what are the key features for that, especially for computer scientists to be able to use that. Now, I mentioned, me back up, yes. I mentioned that new AI edge applications, I know we got to wrap up. I'm going to throw this up here just as an eye exam. When we talk to our students, they get excited about ideas that they come up with to run at the edge. So here is just an example. We have a student who's going to do ultrasonic bat detection, right? What bat is it? I can figure that out, right? I want to understand bicycle usage. Are people wearing helmets? Are they not wearing helmets? Right? I want to understand biodiversity based on audio. There's a professor in Wisconsin who's doing that. So she has a single measure. It's not just birds. It's insects. It's everything. Can I measure biodiversity by analyzing that spectrum out at the edge? So I'm going to do it's going to work. So this is a very super quick example. So if you go to at some point, go to our webpage at portal.sage-continuum. So this is our current map. And we just ended up with a node in Hawaii a couple days ago. So that's really exciting. We also have a node at the northernmost place in the United States, up here in Utqiagvik, which is Barrow, Alaska. But I'm going to show you, we could go down here to this node in Montana. And we can pull it up here. And so over here on the left, you see all the jobs that are running, right? I'm making it really hard from the cameraman now by kneeling at my laptop. So we can see that we're running the sound event detection. We're running the avian bird diversity. And here are all the data blocks, right? Here's all the code. We can look at simple things like temperature, pressure, and humidity. It's also nighttime there, but we can still look at what the temperature of the ground is and what the temperature of the sky is here with the infrared camera. So we could download that image. We could also listen, right? Because we have audio snips that we're taking to process the bird data. And over here under the app catalog, this is our app store I mentioned, right? So this is where if you were interested in writing your own app, you would come over here and you'd say, okay, I want to look at this one here, this avian diversity, and I'm going to click this. And if it loads up here. So we have both what's the science, what does the code look like, how do you get the code out of the repository, and you could go over here to the repository. It's all in GitHub, and you could pull it up, right? And finally, if you wanted to look at the jobs that are running, you could look here at what's running, what kinds of jobs are running, where they're running. This is the postdoc Yong Ho, who's in charge of the scheduler. So it looks like all the jobs belong to him, but that will be fixed, right? Let me go back here and go here and say with that, we'll stop for questions before Satoshi comes up.